Hello, doing some playing with my new to me HP 3561A Dynamic Signal Analyzer, and still learning a little bit how to use it and its functions, capabilities, and um, it's a neat instrument. One of the things I'm doing right now is I'm feeding a 1 kilohertz sine wave at 2 volts RMS into this Behringer DEQ2496, and currently I have all the modules disabled or bypass. So I'm just feeding in to out and looking at what happens when you start to clip the input. And the difference between watching that input clipping distortion on an oscilloscope versus on an instrument like this, especially when you're looking at the FFT in a like a spectrum analyzer type function where you can see the harmonics on a logarithmic scale. With in this case, this is an 80 dB dynamic range, um, is can really show you what's going on far sooner than what you can detect either by ear or on a oscilloscope. And I'll demonstrate that, which is pretty cool. So right now I have 2 volts RMS going into the 2496, and the output's nice and clean. We're going to bring it up just to the point where we see distortion. You're going to see harmonics pop up here. So right about 3 volts is where it's going to happen. I got 2 volts going in. We'll just keep coming up. Keep coming up. 2.6, 2.7, 2.8, 2.9, 3. And you can see at 3 volts we get the clipping light comes on the 2496. And you can see all these harmonics. And in this case, these are even harmonics. So it's going into like a sawtooth type pattern to get the even harmonics. We're just going to back it down just to a point where you can barely see them on here. 2.98. Let's go here. Let's try averaging on. So let's turn averaging off. 2.9, right there, 2.99. Now that's well before you can see and detect any distortion whatsoever in the sine wave on the oscilloscope. Matter of fact, let's up it to where we can just start to see some distortion on the. There we go. I can just start to see some distortion, a little flat topping right here, a little bit of clipping right here at the crests and the troughs of the wave. I can just start to see it. Let's back it off a little bit. A little more. I cannot see any distortion here at all, but we can see it. Now, what's kind of cool about this is this meter has the ability to do harmonic distortion measurements. And by the way, just a little bit of setup. So I'm feeding 1 kilohertz in. I'm looking at 1 kilohertz. My bandwidth right now is set to 12.5 kilohertz total bandwidth, zoomed in a little bit. And we're going to set this up to do a total harmonic distortion measurement. So we'll marker special, define we want to measure harmonic distortion, define the fundamental frequency, in this case it's 1 kilohertz, and then we can see THD minus 74 dBm. Well, a lot of us aren't familiar with looking at minus 74 dBm. We're familiar with the linear measurement and percentage. Well, this can do that. So we can do that. We can go vertical scale, change it from logarithmic to linear. And now it's telling us 0.02%. Not much. Well, since it's a linear screen now, the signal is so minute down here. Let's zoom into that. So vertical scale, define full scale. Let's go to 1 millivolt RMS. There it is. So let's go to, let's go up a little bit. Make this more. So full scale right now is at 2.5, 5 mil. So right now we're at 3 mil. Let's do 3 millivolt RMS is full scale. So you can see the distortion down here in the microvolt range. 50% scale is about, so that's 300 microvolts per division right now. So let's just, this is tiny little bits of signal. So let's go and get rid of some of this digital noise. So go averaging, exponential weights, doing 4 averages. So now we can clearly see our fundamental and our even harmonics. And we're going to extend out the number of harmonics we're going to measure here a little bit, because right now I have it actually calculating for total harmonic distortion of defined number of harmonics. I have it for 4. So let's go up to a few. So defined number of harmonics, let's say 6. Enter. Now it's going to do the additive of all 6 of those harmonics. Let's do a few more. This is 6. Let's go define number. Let's go 8. So that's 8 harmonics. And of course, it's only seeing the evens here. And we're at 0.036, 0.037. So a little bit less than 0.04%. 0.04%. That's not much. It's basically inaudible. But you can clearly see the distortion here. So that's kind of a cool feature of an instrument like this. This is built in the early 80s, throughout the late 80s, and still a very useful instrument. And also I've compared it against my other modern digital multimeters for AC voltage, and it is dead smack on, down to the last significant digit. So it also makes it extremely accurate from basically DC, 0.000125 or 125 microhertz up to 100 kilohertz. And it's an FFT analyzer, early FFT analyzer, limited by the Motorola 6800 processing power and speed, but it's still relatively quick for what it is. Anyways, you can do some pretty cool stuff here. Let's see your vertical scale format. Let's go to, let's see, offset. We can do some cool 80s graphic stuff. So if you have varying signals, you can map it in a 3D plot. So how about that cool retro 80s graphics rastering? Kind of neat. Anyways, neat instrument and still useful today. I'm going to zoom in here a little bit so you can see a little more about the display, what it's telling me here. So you can see we're starting at 0 hertz and stopping here at stop frequency 12.5 kilohertz. We can see this is my marker, and we can move the marker around and look at various points. Let's go here. That's marker at 3 kilohertz. So it's so it's odd. Okay, so we're looking at our odds. This is the odd harmonics. This is clipping, square wave, going into square wave, odd harmonics. So from fundamental 1 kilohertz, there's 3, and then odds beyond that. So, and it's showing us our level of 600 microvolts. And over here, this is showing us our additive of the 8 harmonics. Total harmonic distortion, 0.03839% over here. So just some of the things it shows you. And I haven't played with all the functions on this guy, what all can show you. Let's see here, view on off. What's that? Oh, here's the various parameters. That's kind of cool. Show you basically all the parameter mode that I have it currently set in. And it has memories. You can save and store these traces, and even save and restore various states, instrument states, which is kind of neat. And let's do something else here. Let's go back to, let's hit the preset, which puts it back into its preset default state. Now, let's go again, format, single, just to get the FFT. And I'm going to set this up. I'm going to see if I can do this fairly quickly for a quick 2-tone test. Let me add, I need to add a second tone. So I need to add a cable here. And then I'm going to give it 2-tone of, let's pick here, let's go 700 hertz. On 1 signal generator at 2 volts RMS, And then my other signal generator, we're going to do 1900 hertz at 2 volts RMS. Turn that on. Let me back this up here for a second, or let me do this. So you can see here our two-tone, and what I have set up here in the my signal generator. There's my two-tone. Now, go. Let's zoom into that. So frequency, define span. Let's just zoom in a little bit here. There's our two tones. Let's see here, marker, marker peak, track. Here we go. So that right there is 1900 at minus 0.14 dBV, which is 1 dBV is 1 volt. Or is it 0 dBV is 1 volt? It's one of the two. So we can see our two tones, and we can see virtually over an 80 dB dynamic range, there's no IMD. We can zoom out here to look. We can zoom in or zoom out. Let's go to frequency, span, zoom out a little bit. I see no IMD in there at all. So it's a clean A to D and clean op amps for the input, analog input and output. So of course, if we start cranking up the input to get some distortion in there, we can do that. That's 3 volts. Let's go 3.5. Let's get this thing into clipping. 4 volts, and then let's go with my other generators. Go 4 volts. RMS. Oh wow, there we go. There's some IMD for you. We're going into clipping pretty hard. Let's back that down a little bit. Let's go down to like 3.5 and 3.5. So we're still clipping pretty hard, but that's what IMD is going to show up like. If you look at my oscilloscope, you'll see it starting to flat top and clip. But anyways, neat instrument. Another thing we're going to do real quick, we're going to do a quick frequency sweep. So I have some parametric EQ set up here. As you can see, here's some bands of parametric EQing that I'm doing. This was for a very specific setup for a microphone on a particular two-way radio. And we're going to take a look here. I'm going to sweep the input, and we're going to see what the response curve looks like in the output. So I have my input range set on the analyzer so it doesn't overload the front end, and we're just looking at the sweep right here. Our bandwidth is starting at, our sweep is starting at 10 hertz to 10 kilohertz, and we're going to go over here to average. We're going to go to peak hold, but let's get a little more finite here on the display. So let's go vertical scale. Let's go dB per division. Instead of 10 dB per division, let's go 5 dB per division. And then we're going to go define full scale. We're going to get this down somewhere in the middle so we can see a little more what it's doing here. Here we go. And we're just going to have to let this sweep through because I have it set for 100-second sweep. I could probably speed that up a little bit. Let's go from 100-second sweep. Let's go to like a 30-second sweep. Let's speed that up a little bit. And let's see what we got here. Actually, I want to average, let's go off. Let's go back here, peak hold again. Let this draw. And let's see, this is the actual output. It's a flat input, and this is the output, looking at the output curve after the parametric EQing that I'm doing. Let's just take a look, see what it looks like here. Does it look at all like the parametric EQ on the 2496, and away it does. Yep, this is the big boost that I have here, starting at about 2K. Let's move my marker up. So about 2K, have my big boost. You can see it peaking here at about, it looks like about 4K on the, let's see, 3, peaks right here, about 4, a little more. There's about 4.7, 5K. So it looks very much like it. Of course, this is low frequency stuff down here. I would have to expand this out and look at the dips down here. We can do that, but I'll have to go a little slower sweep and for the low frequency stuff. And let's do that. Why not? Let's turn the averaging off. So let's go here, frequency, define span. Let's go a little lower frequency. Let's say it down to 1 kilohertz. Okay, it's up to 1 kilohertz. And then let's change my sweep generator, maximum frequency sweep to 1 kilohertz. There we go. So we're sweeping between 50 hertz and 1 kilohertz now. So let's see how this does. Let's go here, average, peak hold. I might need to slow my sweep down a little bit to get a little better. Yeah, I'll need to do that. Let's go here, sweep time, 30 seconds. Let's go 100 seconds. Okay. Now, there we go. That's nice, clean. And it's going to take a few seconds, obviously, to sweep this at the lower frequency with this type of resolution. But we can see that's my 100 hertz peak. Move my marker down there. That's my 100 hertz peak on the EQ. Looks like it's actually trying to peak about 80 hertz. And you can see my first cut, 150 hertz. Then my second cut over here at 297, basically 300 hertz, 295, 300 hertz. And it's just going to draw it out up to 1K. I'm not doing much above there. I have to go up a higher frequency to see the boost I'm doing at the higher frequency, but this is 5 dB per division, so you can really kind of see what's going on here. I could zoom in more, 2 dB, all the way down to 0.5 dB per division, but it gets a little difficult to get all scaled on here. Anyways, again, this is a cool instrument. And just to show you, this is the drawn parametric EQ. If I go page, you can see the parameters here, what we're doing. At 76 hertz plus 3, 1/3 octave, then -8 at 149, -5 at 299, and then we don't start to boost again until about 3 kilohertz. And that's how it draws it out. And this is the low frequency, how it actually measures.